So I think I might have mentioned before that the sun right now is ramping up to be as active as it's going to be. Its peak activity, I think March 2013, and then it's going to start being less and less and less active. Now, even when the sun is not very active, it has things like solar wind, those granule features that we saw a little bit ago that kind of look like honeycomb on the photosphere. I mean, those are always there. But things that aren't always there, for instance, are sunspots. And actually, Galileo noticed sunspots on the sun, and it's from the sunspots actually that he could tell that the sun was spinning or rotating on its axis. So the sun doesn't always have sunspots. That means if it has sunspots, it's being active. Also associated with an active sun are solar flares, solar prominences, and I've got some pictures to kind of show you these things. But there's a website out there called spaceweather.com, and it does a great job, among other things, of kind of saying how active the sun is right now. So I just kind of direct you to that. Notice on this website what it also does is related to the sun's activity are whether we're going to see northern lights or aurora borealis. So and right now, that's looking pretty good. So if you click on this map, you can see that, yeah, I'm just now noticing that. If you click on this photograph on spaceweather.com, it shows you these sunspots. So there's sunspots right there and right there. And actually, in our sun lab, we've got a telescope that has a filter on it, so we should be able to hopefully see some sunspots this semester. Just a really good website. Okay, so sunspots, solar flares, solar prominences aren't always associated with the sun, but they are an indication that the sun is being active. And the activity of the sun is related to its magnetic field, or its magnetic fields, its flux lines. And actually, you can kind of see up here, this is the surface of the sun, kind of edge on, and you can see this plasma or gas that's filling these flux lines, these magnetic field lines that leave part of the sun and enter another part of the sun. So sunspots close up look like this. Oftentimes sunspots come in groups called sunspot groups, go figure. And these dark regions are generally cooler than the other part of the sun. But kind of like over here, you can see the regular honeycomb feature called granules, and then here would be sunspots. Kind of pretty, aren't they? So a little bit ago when we saw kind of an arc of plasma, and it was filling magnetic field lines, that's related to sunspots. Okay, so those sunspots, you can kind of see the blemishes here, actually then allow for magnetic field to leave and re-enter in a different sunspot. So sometimes it's so rambunctious that it's called something we call a solar flare. So if you see a lot of sunspots, you may see these solar flares. And solar flares can send charged particles from the surface of the sun. There's something called a prominence, solar prominence, and this is larger than a solar flare, it's my understanding. It's, can you almost kind of see, looks like this material also can, if it's energetic enough, or if there's enough momentum as it's pushed from the surface of the sun, it can leave the sun and head into outer space, hopefully not in our direction. Let me go back here. So prominences are this over here, and then we have something called filaments, and filaments are prominences that we don't see edge on. So prominences and filaments are the same thing. And then we have coronal holes, and coronal holes are they're like conduits through the body of the sun. So there are bright coronal holes and dark coronal holes. And then the big daddy of them all here is a coronal mass ejection. Shortened, we say CME. And you may have heard of coronal mass ejections because if we have a coronal mass ejection that's headed towards the Earth, we could definitely have problems. It takes about 8 minutes for the energy to reach the Earth, but a few days later maybe for the charged particles. So here we have, this might look familiar, these yellow little arrows here are indicating our solar wind, and over here we have the Earth on its tilted axis of rotation, and these pink lines indicate the Earth's magnetosphere. And just to kind of remind you, we talked about this in the last unit of material, but the Earth's magnetosphere or magnetic field actually is a protective layer for us from the sun's charged particles. And I think I mentioned this maybe when we were talking about the Earth's magnetosphere, but just recently that we have put a pair, or NASA has put, in combination with other space agencies around the world, have put a pair of spacecraft out there to study the magnetosphere. Pretty darn cool. So I mentioned this 11-year cycle. So here is kind of the 11-year cycle. And I mentioned that we're kind of gearing up for 2013 being a solar max. So let me take you to another website. And actually we are in what we call Sunspot cycle number 24. And here, this goes back clear to January 2000. And then we have a minimum about the year 2009. Okay. And then we're ramping up to a maximum in 2013. Pretty darn cool. Oops. It didn't stay very long. Let me see if it'll stay. Oh, well, that's okay. Okay, the last slide on this part now, and for this chapter. There's so much more I could say about the sun, but I had to narrow it down, and so this is what you got this semester. So I mentioned that Galileo saw the sunspots moving across the disk of the sun, and then deduced correctly that the sun is rotating on its axis. And the sun rotates, but it has what we call differential rotation. And actually, the Jovian planets, as they spin on their axis, they also have differential rotation. Specifically, the material at the equator is rotating more quickly than the material up near the poles. And so what I kind of liken it to is if you've ever played Twister and you kind of get your arms and your legs all kind of twisted up with other people's arms and legs, playing Twister kind of is what reminds me of what happens to the sun. And over an 11-year, with regard to its 11-year cycle, it gets its flux lines all kind of twisted up, and then all of a sudden it will say, I've had enough, and basically it kind of resets. So the 11-year cycle is related to its magnetic field getting twisted.